and welcome to the seminar this week. Our speaker is Daniele Cozzo, and he will speak about secure, fast evaluation of iterative methods with an application to secure PageRank. Daniele, the floor is yours.
Thank you for introducing me. I'm gonna introduce our recent paper, which is a joint work with Professor Major Smart and Younes Talibirawi. This work will appear at the CTRSA conference in 2 weeks. So, iterative methods have found application to fraud detection. So, to begin with, assume we have a set of bank accounts and transactions between them. Some of them might be, a little portion of them might be illegal, might be fraudulent. And it's in the interest of the banks that own these nodes to detect and prevent such illegal activities. So there are some well-known techniques for detecting frauds that are mainly based on machine learning, but have the drawback that might generate false positives. In order to improve such techniques, recently have been proposed new methods based on graph analysis, so as to reduce the ratio of false positive cases. The idea is that you start collecting these transactions for like 1 month, and you form a graph which is the history of these transactions, and from this graph you extract some features which depend on the topology of the graph. One of these is the PageRank of the graph. The usual way the PageRank algorithm is used, well, it was the base of Google, so its main goal is to measure the importance of web pages according to the number of links and also the quality of links. But here we want to measure something more, something similar, which is something called the reputation of bank accounts. And the criterion is their previous transactions. So the idea comes from an heuristic observation that the transaction network behaves like a web of trust. So individuals are likely to establish relations in terms of payments with those they trust the most. So in a transaction network, honest accounts, honest nodes will look like regularly connected, while malicious ones will look like anomalies in such graphs. And so, yeah, the idea is that the higher is the reputation and a single bank account, and the less likely it is fraudulent. So abstractly, you can think of a transaction graph as a directed graph where vertices are the bank accounts and the arrows are the transactions. And from that, you can get the adjacency matrix, which is which you can turn into a row stochastic matrix P by dividing each entry by the number of outgoing arrows. So being a stochastic matrix, you know that the largest eigenvalue is equal to 1. It might have multiple eigenvalues equal to 1, but all of them are bounded by exactly 1. In general, they might be complex numbers. And also, you consider at a certain point the event that the money at any point might be transferred to any other account with uniform probability. This is an event called random surfer model in the context of the internet. But here it really gives the idea intuitively that money will be saved by the bank account. So the effect is that we get this matrix M, which is still row stochastic. It's a convex combination of two stochastic matrices, and the eigenvalues are related to the ones of P by lambda. So lambda is a public number between 0 and 1 called damping factor. The interesting thing is that with this transformation, we get in technical terms, primitive matrix. So we are sure that we have exactly one eigenvalue equal to 1. The matrix M now can, models exactly a stochastic process. So the graph is completely connected, and we can, computing the PageRank of such transaction graph is exactly like finding the stationary point of this Markov chain, which can be done using the power method. So you define this sequence, and the stationary point, which is unique, is then given by the limit of such sequence. The entries, as I said, can be interpreted as the reputation of the bank accounts. And once this algorithm is performed, you want to investigate the bank accounts that have a low entry, a low value. Okay, this was clear when there was only one bank that owns all the nodes in the graph. But what is not clear is how this can be performed when you have many banks, different banks, each one owning a portion of the bank accounts. This is because each bank can only see the transactions that somehow involve their own clients. And this concretely means, for example, that the green bank can only see a part of the matrix, and the rest is secret. It's blank. So it's clear that for fraud detection, in real cases, banks need to collaborate, need to share their data in order to perform this algorithm. But the problem is doing that while preserving the privacy of their clients. And this problem can be solved using privacy enhancing technologies like homomorphic encryption and multi-party computation. A paper from Financial Crypto 2019 gave a protocol based on homomorphic encryption, suffering from some issues, passively security, and also it worked with assuming that most of the parties involved were honest. And the very design of their scheme forced the computing parties to stay online for the whole process. Here we propose a multi-party protocol, a protocol entirely based on linear secret sharing that aims to solve all these issues. So the idea is that it would be great if we had an ideal functionality F, which can be used as a black box from the banks. So they just send their private inputs to F, and F performs its task, which in our case is computing the PageRank of the transaction graph, and then simply sends back the output to the banks. This is completely secure because it's used as a black box and F is uncorruptible. Yeah, but such a thing in reality does not exist. So what we do is we design a multi-party protocol which implements F, meaning that it behaves like as a black box like F. It gives the same output, so it's correct. But it's an interaction, so the parties interact. So this interaction might leak something, and the security requirement is that it doesn't leak more than this scenario. So the only thing that was leaked here was the public description of the problem, as well as the output, the PageRank. So the security is that parties, the banks, shouldn't learn the other bank's inputs and anything except from what can be learned from these public parameters. So a key building block for our protocol is linear secret sharing, which consists in additively sharing secret feed elements among the banks, the parties. And this representation is invariant under additions and can be used also to force to work with multiplications with some additional effort, but you can, it's a universal way of computing. So you can do additions and multiplications. And you can construct protocols that achieve active security, allowing aborts, even when just a single party is honest. but most importantly, it allows the parties to outsource computation, meaning that you can have many banks that can share their secrets in such a way that only a few powerful servers are really needed. So back to our original problem, the entries of M are rational numbers, if you remember how we got them. This is not a problem because linear secret sharing can be adapted to deal with such numbers using fixed point notation. And basically, so we have then an arithmetic circuit. So the only thing that we need to do is to express the function we want to evaluate as an arithmetic circuit. So we want to express the power method as an arithmetic circuit, which is quite easy. So each iterations consist in m squared plus m multiplications and m squares additions, while the whole circuit will somehow depend on the number of iterations needed for convergence. So the question is, how many iterations do we need? So the easy way to overcome this question is we fix n to be 100 or 30, depending on the application. Different applications to require different, take different times to convert for convergence, and we just execute the algorithm in a secure way. This does not leak anything because n is fixed. But of course, we might do more iterations than needed. So of course we can improve this by fixing a small error, and then stop iterating when the difference of two consecutive elements of the sequence are less than the error epsilon. So this, of course, is optimal, but introduces a security problem because we are revealing the number of iterations. So we might leak something about the secret matrix M. However, the effects are as you expect, are really good because we can save a lot, and these are the running times of our experiments. So just to explain you this table, this is the number of bank accounts, number of parties, that is the computing servers actually. These are the running times for a fixed number of iterations in terms expressed in seconds. All right. So, and here we just we perform the same algorithm by terminating easily the iteration. So you can see, as you expect, the running times are much better. But however, we have this security problem. We want to quantify the amount of information that we leak by revealing the number of iterations. So for the power method, we can write down the general term, which is like this. from which you can see that the convergence is really given by this ratio, this second largest eigenvalue over the first eigenvalue. That in our case, having a stochastic matrix, it's just lambda2. So the number of iterations leaks one sample from the geometric distribution with ratio lambda2. So what about the second eigenvalue? So this is a quite known paper from the early 2000s, which analyzes the Google matrix, a fancy name for the matrix I introduced at the beginning. And they found out that according to the topology of the transaction graph, we might have two different cases. Either, okay, we have a graph where we can find at least two closed irreducible connected components. And they proved that lambda2, the second largest eigenvalue, is exactly equal to 1 minus lambda, the damping factor. And this being public, we don't leak anything, because we are leaking a sample from a distribution that depends on lambda2, but this is already part of the public parameters. So there is no leakage in this case. Or we can have a graph where there is only one closed irreducible connected component, for which we can only say that in modulus, the second largest eigenvalue is less than 1 minus lambda. So we are leaking one sample from the geometric distribution that depends on lambda2. But this is not a problem, because it's almost of no use for an attacker. The only way you could exploit this is collecting many samples from this distribution. And in our application, the banks will only perform the algorithm, will only compute this, the PageRank of this for this graph once. So this information is negligible compared to the size of the graph. To conclude, one can formulate a more general problem. So so if you have a contraction, and you want to solve a fixed point problem, and you want to ask whether revealing the number of iterations needed for convergence to the fixed point, revealing that is safe. And the answer is that it depends on the application. So if F is given by a matrix, as we saw, this is connected to the number, so to the samples from the geometric distribution that depends on these two secret things. And in the more specific case, when we have the Google matrix, then either we reveal a single sample from a distribution that depends on lambda2, which I already said that is a negligible amount of information leaked, or if we are lucky, we have a graph which has only has more than two closed irreducible connected components, and we don't leak anything because lambda2 is already part of the public parameters. And that is the end of my presentation.
Thank you, Daniele. Do we have questions?
Maybe a stupid question. Danny, can you show the table that you had your performance? So yeah, this one. So here you have random graphs and the banking graphs. By banking graphs, you mean they are real, let's say real graphs that we have in current financial systems, yes?
Kind of, hopefully. We simulated them since we don't have access to the actual graphs because they contain sensitive data.
So how you sample these random graphs? I mean, what is the distribution that you pick for the? We
picked the uniform distribution. We generated random graphs at random.
Okay, uniform random. Okay, I see. And the number of parties basically are the number of banks. Yeah, 2 banks, for example, in the first row.
Yes and no. It depends. Yes. Actually, the number of parties that are meant to perform the computation, it might be servers.
Okay.